Hi class, we are on the last two sections of chapter 12. I've combined them because both do not have a lot of slides to them. First one is discussing the different types of crystalline solids, and then we're going to go over a review about water. So first we're going to start off with solids, and we have classified solids as either crystalline, which is well ordered, very patterned, long chains in a sense of atoms and or molecules. And amorphous, which are not ordered, they're very disordered, they're kind of jumbled up together, so they're very different from each other. And crystalline, on top of being well ordered pattern array of atoms, we can also divide that even into more of three different categories of molecular, ionic, and atomic, based on the units that compose that solid up. So that's what we're going to look at here. We're going to break this down. So we have crystalline solids. We have three different types. We have molecular, ionic, and atomic solids. These are molecules. They have low melting points. These are called formula units, and that involves ions. So what we would call a lot of things, we call it molecular mass. For instance, if we wanted the mass of a molecule, we would want the mass of an ionic compound. We actually say formula mass, and formula means cations and anions, but people get lazy and just say molecular mass for everything, including myself. I do it. Atomic solids are made up of atoms. So those are molecules, ions, and atoms, and these have variable melting points. So the first thing we're going to look at is molecular solids. And molecular solids are molecules, obviously. So an example is ice, which is solid H2O, and then dry ice, which is carbon dioxide. Those are two examples of molecular solids. Excuse me. Molecular solids are held together by intermolecular forces. They all have dispersion forces. Depending on polarity, they can have dipole-dipole forces, and some, if they meet the specific conditions, will have hydrogen bonding. Ice is held together by hydrogen bonds. That's what makes ice different from any of the other compounds that have around the similar molecular mass. And dry ice is held together by dispersion forces. That is why it, excuse me, remember, all the compounds have dispersion forces, but after that, then they differentiate between dipole, or some of them have dipole if they're polar, and some of them have hydrogen. So ice has dipole, dispersion, and hydrogen bonding, but it's talking about the greatest, when it's only telling you about hydrogen bond, it's telling you about the strongest force. That's the one that it's pretty much labeled as. That's the one that's giving it the behavior and the look for how it is. Dry ice, if you've ever dealt with dry ice, once it's in room temperature, it sublimes away. It goes from a solid to a gas. And that's because dispersion forces are very weak. Molecular solids tend to have low, moderately low melting points. This is true because CO2 is dry ice is a perfect example. That is solid carbon dioxide. Its melting point sublimes at negative 78 degrees. So the minute we take it out of a negative 78 degree freezer and place it on a countertop, it will immediately start to sublime, because let's say the average room temperature is around 70, 72, 75 degrees, which is, I think if I'm right off the top of my head, I'm probably wrong, which is around 23 degrees Celsius. So obviously it's going to immediately go into sublimation and become a gas. And that's what happened with the gases. The gases that we know are gases are not always gases. We have to get down into really low temperatures to get them out of that gaseous state. And since we can't survive at that, that's why we only understand them as gases at the temperature that we're at. Ionic solids. These are probably the easiest to understand because they're ions. They have opposite charges, and that's what we call electroattraction or electrostatic attraction. And these are excuse me, I can't clear my throat. These cations and anions, these attractions hold them together, and they're very, very strong attractions, these ionic bonds. So they're very hard to break. If you've ever tried to melt salt or boil, it's the temperatures of these, that the energy that has to go in to break these ionic bonds is really high. And you see that they're very patterned, and it's called a solid lattice structure. That's what this pattern is. These are all covered by the opposite charges, and that keeps it with all these ionic bonds and keeps them strong. So the forces that hold ionic solids together are actual ionic bonds. These ionic bonds are stronger than any of the intermolecular forces. That's why they have very high melting and boiling points, higher than anything that has intermolecular forces, because they're not dealing with forces, they're dealing with ionic. This is the opposite charges, the attractions that are holding them together. They tend to have very high melting points to molecular solids, and most, if not all, ionic compounds are solids at room temperature. Solid sodium chloride, it melts at 800 degrees Celsius, while carbon disulfide, a molecular with a high molar mass, melts at 110 degrees Celsius. And that has to do with the fact that carbon disulfide is nonpolar and is dealing with dispersion forces only, yet, excuse me, an ionic bond is extremely higher bond attraction than what intermolecular forces have. Atomic solids are solids whose composites are only atoms. So diamond, which is carbon, iron, and solid xenon are good example of atomic solids. So diamond is all carbons. Atomic solids can be divided also into three categories, and these are covalent atomic solids, non-bonding atomic solids, and metallic atomic solids. So when we look at these, we'll look at the next page and there's a chart. So the atomic solids are broken down to three different groups. We have covalent, non-bonding, and metallic. All different type of forces, a different kind of forces under these atomic solids. So covalent, they're held together by covalent bonds. They have a high melting point. Non-bonding are held together by dispersion forces. Dispersion forces, remember, are the weakest of all the intermolecular forces. And all molecules or atoms have those, and that's low melting points. So this covalent has a higher melting point than non-bonding. And then we have metallic, which are held together by metallic bonds, and they have variable melting points. So we're going to take a look at that. So if we look at diamond is all carbons, and it's carbons that have, remember, they share electrons. That's what covalent means. And so they have covalent bonds. So they're sharing with other carbons. And throughout them, they have 4 covalent bonds, and those are connected to 4 other carbon atoms, and this eventually goes into a tetrahedral geometry. So these these bonds keep it very ordered and very strong. So covalent bonds are strong. So if you think about that, diamond is estimated to melt at 3,800 degrees Celsius. That is very high. That's high compared to something that is like ionic bonds. So this is very high, and if you didn't know, diamonds are very strong. So these covalent bonds really keep this together very well and make it incredibly strong. And it has to do with the hexagonal pattern as well. So all the patterns and how these bonds are situated allow diamond to be as very strong as it can be for covalent bonds. Non-bonding atomic solids, such as xenon, which is a noble gas, are held together by very relatively weak dispersion forces. Remember, dispersion forces are the weakest of the intermolecular forces. It has a stable electron configurations. If it's a noble gas, it obviously will, which means it's extremely stable. And because it does have that, it doesn't need to bond with anything else because it's got the octet. It's going to meet the octet, doesn't need or doesn't want to bond with anything else. But just because it's stable doesn't mean it has transfers to other areas. So for instance, it doesn't have a high melting point. It has a very low melting point, which is approximately 112 degrees Celsius. That is because it only has dispersion forces. And remember, everything has dispersion forces because they have electrons. Metallic atomic solids, such as iron, silver, and lead, have variable melting points. Metals that are held together by metallic bonds are the simplest model. They consist of positively charged ions of a sea of electrons. They have varying strengths. So, for instance, mercury has a melting point below room temperature, which makes sense because mercury is a liquid, and that's how we see it. If you look at a barometer for pressure, it is a liquid. You know, I am a 70s child. We used thermometers that had mercury in them. So we got used to liquid, to seeing this strictly as a liquid. We don't, it's one of I believe it's the only metal that's a liquid at room temperature. Other metals such as iron have relatively high melting points, which is why you think about if you have an iron skillet, you can heat it very high and it really does nothing to the pan. And that's because it can handle that much heat. The iron is not going to melt on your stove. So depending on which type of metal, they can have high melting points, low melting points, or something in the middle of that. And these are held together by metallic bonds, which consist of positively charged ions of sea of electrons. So if we look here, this is a simple model of a metal, and each atom donates one or more electrons to this electron C. The metal consists of the metal cations in a negatively charged electron C. So we have, if you see the pluses, make sure you understand, and then we have, excuse me, I'm mumbling here. So here we have the cations, and then we have the electrons that are around it. I'm not going to really expand on this more than what you are reading about, because in my opinion, it doesn't really give a good explanation of this. So anything that's going to be asked is going to be straight from this reading on this subject matter here. Okay, so let's take a look at this. Identify each solid as molecular, ionic, or atomic. So for the first one, we have calcium and we have chloride. It is a metal and a non-metal. Anytime you have one from one side of the periodic table and one on the other side of the periodic table, that is an ion. So this is an ionic compound consisting of a metal and a non-metal, and it is creates an ionic bond based on the opposite charges, the attraction to them. And so calcium chloride melts at 772 degrees Celsius. We have cobalt in the middle, and that is a transition metal. That is a metal, and therefore it is an atomic solid because it is by itself. Cobalt melts at 768 degrees Celsius. And here we have carbon disulfide. All of that consists of nonmetals. They are all on one side of the periodic table. This is a molecular compound. It is nonmetal bonded to nonmetal, which means that it is sharing electrons, and this is therefore molecular solid, and it melts at negative 110 degrees Celsius. Okay, so water. This is all going to pretty much be repeat information that I've already discussed. Water has a low molar mass. However, it is a liquid at room temperature compared to everything else that has molar mass of that same value or even greater than this value, and they are still gases at room temperature. It has a relatively high boiling point compared to other structures, compared to compounds that match that molar mass. All of that has to do with how the molecule is shaped, the partial positive, partial negative, and hydrogen bonding. So the bent geometry of the water molecule and the highly polar nature results in the molecule with a significant dipole moment, which remember, it means a separation of charge, and that is the partial positive and the partial negative there. That allows other molecules to come aligned to it because of the bent nature, and this creates a hydrogen bond. And remember, hydrogen bonds is specific. It has to be attached to an oxygen, fluorine, or nitrogen, and then be attracted to another molecule that has an oxygen, nitrogen, or fluorine on it. So that's the only type of hydrogen bond that exists, and the hydrogen has to be attached to one of those oxygen, nitrogen, and fluorine. So this allows this very strong hydrogen bond between them, which other molecules in the same molar mass do not have. And that is why we have water as a liquid. The force and the attractions between the molecules allow this to be a liquid at room temperature. The water's high polarity also allows it to dissolve many polar and ionic compounds. And then it can pull those compounds, those ionic cations and ions away from each other and hydrate them, meaning completely surround them so that they cannot go back together with the opposite attraction. So the polarity, or let's say the water's attraction to the ions, is greater than those ions coming back together, the attraction between them. Water is the main solvent in living organisms. I think that's pretty obvious. We should know that by now. Water, the way water freezes, is also extremely unique. It is unlike any other substance that we know of. And that's because it contracts when it freezes. It expands upon freezing, and everything else when freezing actually does not. It does the complete opposite. This is why water pipes burst, because it actually gets bigger and not smaller. Where everything else gets smaller, it constricts. So when water freezes, it pushes out. The water pipes burst because of this. Because liquid water expands when it freezes, ice is less dense. So the actual water as a solid is less dense than water as a liquid. This allows the water on top of ponds and air lakes to freeze while everything below it stays insulated. Water reaches maximum density at 4 degrees Celsius. Ice cubes and icebergs float. The frozen layer of ice at the surface of a winter lake insulates the water and allows everything that lives underneath it to be insulated and fine and normal. If this ice layer were to sink, it could kill bottom-dwelling aquatic life and could allow the lake to freeze solid, which we don't want. The expansion of water upon freezing is one of the reasons why most organisms do not survive freezing. When water within a cell freezes, it expands and ruptures the cell. Same as water pipes bursting from, water causes pipes to burst. Let me fix that. Many foods, especially those with high water content, do not survive freezing as well. I mean, if you've ever tried to eat something that was frozen and you can tell that the freezer burn got to it and so forth, it is not good. Industrial flash freezing of fruits and vegetables happens so rapidly that the water molecules cannot align into expanded phase, and so the cells are not ruptured. So it prevents them from coming into a pattern, which allows the solid water to occur. Because if you look at an ice cube structure, the water is very patterned out and very aligned. And that once it's aligned, then it can allow it to expand because of that pattern. And industrial flash freezing prevents that from happening. So this is a review. We have different type of intermolecular forces. We have dispersion. Everything has dispersion. Some have dipole, and that has to do with polarity. Excuse me. If the molecule is overall polar. Hydrogen bonding, I've already gone over that a few times. We have crystalline solids, which is molecular solids, ionic solids, and atomic solids. And then we have water. That is why water is what it is because of strong hydrogen bonding. And it freezes, it expands when it freezes, where everything else contracts. It is very polar.